chapter 12, page 376, is entitled Interference of Sound Waves. So in your textbook there, you see, on page 376, you see a stroboscope photograph of a vibrating tuning fork. Okay, so we've talked a lot about tuning forks, and if you look at the diagram there, the tuning fork at the times, vibrate in and out. They make compressions and rarefactions, and the waves emanate out from the tuning fork. When waves collide, we have seen how they overlap and interfere with each other, either constructively or destructively. Now, if we just stop for a moment on these two words here, constructively, when we talk about principle of superposition, remember we did that lab and we did that assignment where the waves and you combine the waves. If the wave gets larger, right, you have a wave like this and a wave like this, the resulting wave is larger, right? That is constructive interference. If you have a situation where the wave is, you have a positive pulse and a negative pulse, get rid of those, okay, and you have a negative pulse here, then those would combine to be, fairly destructive, right? They don't add to a larger wave, they add to a smaller wave. So that's destructive interference. Constructive versus destructive. This is true, this is especially true of identical waves. So if you have two identical sounds, you will be able to sense with your hearing either the combination of loud, a louder signal, or a softer signal. And actually what will happen is it will kind of oscillate from loud to soft. You'll hear the woo, 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 woo. You'll hear that kind of that sound where it's like louder and then softer, and it won't be a pure tone when we talk about sounds. Many sounds radiate from a source in a spherical pattern. So if you have a speaker or something like that, or a sound source, a person talking, the waves sort of emanate out just like they do when you drop a rock in in a pond, right? A very still pond or in a still lake, you see the waves emanate out from where the rock hit the water. Two sounds that are identical and near each other, they will produce overlapping wave patterns. Okay? And if you want to just check in your textbook real quickly for an overlapping wave pattern diagram, this produces areas of high intensity and low intensity. So if we look at some diagrams of wave interference, here's a diagram or a picture of two rocks or two objects that would have been dropped into water, right? And you can kind of see, and you can imagine if this was a video, you could imagine those waves emanating out and they would interfere as they collide with one another. What's interesting here, and we're going to talk about how this works with light a little bit later, but you see how there's really a bright ring right here and there's really dark rings in between the bright rings? You see that? What this is doing is that these waves are actually bending the light to actually kind of steer the light away from this region that looks dark and towards the region that looks really bright. And you would see here where they overlap, there's bright spots and dark spots. So if we go back to, let's say, a diagram like this is pretty funky right here. But you can see that there are some really dark areas. See the really dark spots there? There's really bright spots as well. So that's constructive and destructive interference. All right, so here's the example of source 1. That's the green spot right there. Source 2 is the other green spot over there. And they are making identical sounds at identical frequencies. And each of these semicircular lines here represent either a crest or a trough. And so if we look here, and I'm just going to try and highlight, this would be, if it's dark, it would be, we can say that is a crest. Okay, so there's a crest, and here's another crest for the waves that are emanating out from source 1. Okay, so you see this here. So these are the crests that I'm highlighting here. On the other source, if we're talking about a wave, and you think about the sound wave, the compressions would be the crests, and these would be like the troughs, right? The rarefactions. And compressions and so on. Or it would be like this, high intensity, low intensity, high intensity. So the crests would be the dark spots. And this is going to get a little bit busy, but I'll try. So here is the crest for the second wave pattern. Another crest. And another crest. You see that, how they're going out like that? So in this case, we would have areas of maximum intensity are the red dots, where a crest meets a crest. See? There's a black line from the one source and a black line from the other one. Crest meets a crest. Crest meets a crest. Crest meets a crest. Where a trough meets a trough, okay? So you can see how it would be, superposition, right? It would make a maximum intensity of two waves combined, a crest and a crest. This is the resulting wave. Or a trough and a trough. That's the resulting wave. So this would be, maximum intensity would be constructive interference, okay, at these red spots. So a trough and a trough, a crest and a crest. The blue spots would be where there's minimum intensity. That means where there would be destructive interference. So you have a crest and a trough. All right, so I'm just going to erase here a bunch of stuff so we can kind of start over. But where a crest meets a trough, so see there's the black line and a little skinny line there. So that is destructive. The blue dots are destructive. Okay. Now, if you think about this as a whole, and you think about sound, okay, when you have two speakers, like let's say you're listening to music, and you have two speakers that are side by side like this, and they're both facing the same direction. This would be an example of source 1 and source 2 here, both going in the same direction, right? And what would happen is you would be able to, if they're playing the same music, which two speakers playing the same music, that would happen, right? You would be able to find a space where it would seem louder, and then another space where it would seem quite a bit quieter. And they would be right sort of close to each other. This is why, like in a auditorium, in a church or at a concert even or something like that, if you have speakers, that are faced the same direction, they are going to interfere. The sound's going to interfere a little bit. And so you might have pockets where it's really loud or pockets where it's really quiet. And they could be literally within feet of one another. And so that's what this means. That's the physics behind it. You have a crest and a crest making a loud region, and you have a trough and a crest making a quiet region. Okay? So this is why it's a bit of a art to make sure that the speakers are not pointed towards each other for sure, but to make sure that they're kind of pointed away from each other so there's minimal interference. Right? So you see, if things are done right, the speakers are sort of close together but pointing away from each other, and they're not far apart and pointing towards each other. Now, sometimes you can't get away from that situation, but to minimize interference would be the goal. So the notes to accompany that, a crest and a trough overlap, they cancel each other out, and that is a quiet spot. Okay, so a crest and a trough produces a quiet spot. A crest and a crest, they would produce a loud spot because it would be an increase in amplitude there. And of course that's just like the superposition of sound. So of course this could happen in with a single sound source as well. Okay, if the sound is reflected, if there's an echo or if it's reflected off walls or ceilings, then there would be this kind of interference as well. Okay, so you could have two sound sources, or you could have one, and with that reflection, that would cause the same sort of thing. Okay, now again, if you don't catch up to the notes here, we can either go back, all right, when two waves collide, they interfere with each other. We've looked at how identical waves can cause an interference pattern. like this, when they collide with each other. When two waves of different wavelengths overlap, you get a reoccurring pattern of interference. Sometimes they add constructively, and sometimes they add destructively. And so here's a diagram we'll just take a minute to look at. You can see that this wave here, all right, is slightly, it's not an identical wave. What's different about it? I'll let you maybe tell me. What's different about this wave versus this second wave here? What's different? It's what? Okay, it's off a little bit. Okay, so you're saying the crests and the crests don't exactly line up. Okay, well they kind of line up. Maybe here. Maybe close. What else? What do we say up in the notes here? Different what? Okay, so the different wavelengths. Remember, that's from the start of a wave to the start of the next wave, or from the start to the end. Okay, so there's the distance there, and here is the distance here. It's slightly different. Okay, it looks like the frequency is different as well. So if you combine these waves, and they've done the superposition assignment here for you. They've overlapped these waves. This is the resulting wave pattern that you get when these two are combined, when they're played over top of each other. This is the resulting wave. So you can kind of see that we have a region here of high amplitude, and then we have a region of really low amplitude right here. You see that? And so when these tones, or when these sounds are played and they are allowed to interfere, you get these rises in amplitude and then drops in amplitude, and it kind of happens in a reoccurring pattern. So the image above is the two top waves are the original two frequencies, the bottom is the resultant wave. Notice that it follows a repeating pattern. So this is sort of the envelope of the resulting wave. Okay? And you get this loud spot, and then you get a little quiet spot. If you were to draw a wave around, you would get what is called the beat envelope. Okay? The beat envelope. The nodes in the beat envelope right here are the quiet points, the nodes, or the quiet parts. The antinodes are the loud spots. So this would be an antinode right here where it's really loud. Okay, the opposite of the node. This would create a beat frequency. The closer the two frequencies are to each other, the fewer beats they would produce. So this is the formula for beat frequency right here. And of course, you know what these vertical brackets mean, right, from math? That's absolute values. There's no positive or negative to this. And the beat frequency would be simply the difference between the two frequencies. That's what it is. It's just the difference. So if you've got two different frequencies, then whatever their difference is, that's what the beat frequency would be. This simple principle is used to tune musical instruments. If two things play the same frequency, then they should not produce any beats. There should be no beat frequency. There shouldn't have a wah. Now, this is used to tune a piano, okay? Used to tune a guitar. And I'm going to give you a little demonstration in the back there with tuning the guitar using harmonics, and you'll be able to hear the beat frequency. This is sort of how it's used, okay? So I'm going to give that a shot here. So we talk about mechanical resonance. Resonance is the main word here, and mechanical is the type of resonance. So it would be good for us to understand what resonance is. Okay? On page 387, your textbook, again, the definition says, resonance is the response of an object that is free to vibrate to a periodic force with the same frequency as the natural frequency of the object. So if we want to summarize what resonance would be, it would sort of be a natural frequency, okay, that an object exhibits, okay, when another force is exerted on it. So resonance would be, let's say, a response to an external force causing an object to vibrate at its natural frequency. Okay, so if there is physical contact between the periodic force and the vibrating object, it's called mechanical. So if you're rocking a car in the snow, if wind pushes on something, it's mechanical. So resonance is this response to vibrate at a natural frequency. Mechanical resonance is caused by an actual, physical contact. So mechanical, or let's say physical. So in simple terms, mechanical it means like physical contact. So there's if you're pushing on a car, if you're rocking a car because it's stuck in the snow, you're pushing on the car, and as it moves, it is kind of naturally moving. It goes one way, and then gravity or whatever pushes it back, and so you get it moving, and you match that back and forth. That's mechanical. You're actually touching it. So if you look at the picture at the bottom of the page there, it's a picture of the Tacoma Narrows Bridge. And the Tacoma Narrows Bridge, wind actually we're pushing on the bridge, and the bridge was not built to withstand the forces of the wind, and the bridge, having a large mass and lots of inertia, it was free to move, and so there was a natural sort of frequency that this bridge could actually move at, and that amplitude got bigger and bigger in this windy day, and you see. And I'll maybe try and find you a little clip of that. But you'll see that this bridge just started to go. It just snowballed. It just started to move and rock, and eventually it broke. But that's basically the resonance. The bridge had a natural frequency of movement, and it wasn't stabilized enough, and so that movement just kind of kept building and building. A really old video of it, but see the bridge there? Suspension bridge. Look at that. Look at that car. The crash. And so obviously the structure couldn't take it anymore, and there comes a point where the drama builds. Look at the amplitude of that wave. Look at that. You can just see it transverse wave. This guy doesn't care right here. He's like, I don't care. I gotta get to work, man. This is an exciting movie. What's gonna happen? Oh, look at this goof. Yo, you might want to get off the bridge. You see, that's not normal. He's like, dude, I got candy in my car. I gotta get back for it. Get off the bridge. I'm sure he's thinking it's just gonna die down here. Okay, look at that. This guy's totally chill right there. Yeah, the guy with the camera's on the bridge too, I guess. It's kind of dumb. Boy, this music is just getting exciting. Uh-oh. Check it. Oh, look at that. Boom. Done. Didn't think that was going to happen. Some engineers lost their job that day. Okay, that's a sucky bridge. Look at that. You just gotta go really fast in this section and you'll probably be able to make it. Okay. You know what I'm saying? Alright. You too. Ooh. Scary. Okay, so Tacoma Narrows Bridge, there you have it. Tacoma Narrows Bridge. Interesting. Okay. An oscillation, you guys know what oscillation means? If something oscillates, it goes back and forth. Back and forth. Okay, oscillation. An oscillating fan, don't need one here today because it's freezing, but an oscillating fan, the fan moves side to side, back and forth. Okay? So, periodic motion. Okay? Oscillation. Sonic booms. So why don't you go ahead and just take down some of these notes. We talked about sonic booms. I've showed you a video, aircraft flying by. Remember we talked about speed of sound, what happens when an aircraft approaches the speed of sound. This is exactly what I was talking about here before. Here's a stationary object right here. Okay? It's like a sound source that is not moving. This sound source is moving. This would be like a car driving down the road at a high speed. Okay? And what happens is the sound waves are emanating in every direction from the car. And if this is an overhead view and the car is driving this way, okay, the sound waves are kind of piling up a little bit here, right? And so the frequency actually changes here. And we're going to talk about something called the Doppler Effect as well. And I think that will be right after this. But you can see that the waves are piling up here, and actually the waves are being pulled apart in this back area. But what a sonic boom is when the object is traveling faster than the speed of sound, and it actually breaks through this area of really high compression. Okay, so this is a very dense area, and you saw in that video with the aircraft how it kind of formed clouds around the airplane, right? When it got to that high speed, there was like this sort of almost like a conical cloud that was forming on the aircraft, and it was compressing the moist air, and it was actually forming a cloud. The moist air was forming a cloud. And so what happens when an object passes through there? Okay, let's just take notes here. Okay, a fast-moving object, faster than the waves are traveling from the source. So the object is actually moving faster than its sound can travel. The waves then overlap each other, and they constructively interfere along these lines. So you can see how now we're talking about the sound waves from a single object are actually allowed to superimpose on themselves. And so, if you think about these circles as, crests or areas of high compression, look at how they overlap here, and you have these, it's actually in a conical shape, it's in 3 dimensions, but you can see you have these areas of high compression and high amplitude, and that's when you kind of hear that explosion, because it's just a real intense compilation here of these lines. So, just going over these drawings again, a rock is dropped into the water, right? The second might be a slow swimming duck. You've seen that on Wascana Lake there. A goose swims or a duck swims or something like that, and you see you have these little ripples in front of it, and they big, wide, ripples behind it as it's moving. Right? Since the waves in the water are not that fast, this could be many things like a fast-moving canoe or even a motorboat. The waves that are constructively interfering create what is called a shock wave, and that's the boom really that we hear, the sound, the explosive sound. It has a sharp increase in amplitude. So a shock wave is a sharp increase in amplitude. If we're dealing with sound waves instead of water waves, the object must be moving faster than the speed of sound in order to cause them to interfere. This is what happens with some aircraft, bullets, rockets, etc. Okay? Now, if we go back to this motorboat example, now obviously water waves would travel much slower than sound waves, right? Pretty slow. You drop a rock in, the waves go out really slow. So if you think about a motorboat, if it's just idling along, right, you've got waves piling up. But what happens when the motorboat goes pretty fast? Do you know how those waves, it causes a wake and there's all that disturbance on the side of the boat? Well, really, those waves are sort of piling up on each other. That's a similar example to what's happening when an aircraft or a bullet or a rocket travels faster than the speed of sound. Okay. The question here is, when do we call a shock wave a sonic boom? Let's find out. Make this a little bit bigger for you. Since sound travels away from an aircraft in all directions, up and down as well as sideways, the aircraft produces a sonic boom, shock wave, in the pattern of a cone, with the fast traveling object at the tip of the cone. So, remember when we saw those pictures of the aircraft, and it seemed like there was, little conical shaped clouds forming on the wings, the wing edge? What this is saying is that the object and even the tips of the wings and that sort of thing would cause their own little sonic booms, or those pieces of the plane would also be a part of this. There's an interesting note here. The aircraft produces a sonic boom shock wave in the pattern of a cone. All parts of the aircraft that are cutting through the air will create their own sonic noise. These noise cones sound like thunder when an observer passes through them because of the sudden spike in air pressure. This can powerfully shake an object and cause it to shatter. And you saw what the wind did to that, to the bridge, right? Over time, it just kind of kept shaking and getting bigger. Well, if you think about that on an aircraft, if the wings are sticking outside, if the wings are out too far, then this pattern right here, okay, if the wings are in this area, guess what? That's an intense pressure area, and that's going to cause them to vibrate a lot. So that's what this diagram is about, actually. When designing objects, you ever notice how really fast, planes, like jet planes, they're kind of shaped a certain way? If we're talking about a fighter plane, right? The wings are laid back quite a bit, right? Right? So we have this sort of thing happening, right? Sort of. They're not like this, okay? The wings don't stick out like this so much. They kind of go back, right? You ever notice that? So if a plane is traveling really fast and it's going to break the sound barrier, you don't want to have any parts of the plane in this area here, because that's going to cause the wings to basically rattle off. It'll explode them. The tips of the wings will explode. So that's why, yeah, that's kind of a bad drawing. Oh well, too bad. I try to get fancy, that's what happens. So an overhead view of a plane, right? Wow, what was that? Hit the wrong button. Okay, let's see if this is any better. Oh yeah, the old pizza plane. Okay. All right, something like that. There's the guy inside. He's saying hi. Okay. All right, so look at this. The shock wave here will go past the wings. It's not going to rattle parts of the plane off. This guy is pretty happy. Okay. Hi, I'm happy. Okay. The aircraft above, this one right here in the black, the wings will most likely shake off if it passes the speed of sound. Most aircraft will generate two sonic booms when they fly, one from the front of the plane and one from the tail of the aircraft. Interesting note. Okay, so make sure you get these notes in here. This part was just for interest's sake. When designing objects that travel faster than sound, they're careful that no object, part of the object generates a sound cone where another part of the object will be passing through. That's why this guy's happy, this guy's not. Okay, so finish up those notes. That's the lesson for today.